Right, we're going to look at some basic cable resistance calculations. So, for example, on site you have just installed a circuit as per the design, and you want to confirm that the resistance value for the conductor that you're about to measure is the correct resistance. Okay, so either prior to or after testing, you can pop out the calculator in your on-site guide or guidance note 3 and do a quick cable resistance calculation just to confirm that your measured values are true to the design. So in your guidance note 3 in Appendix B, or in your on-site guide in Appendix I, the first table that you'll find in there is the milliohm per meter value for your conductors at 20 degrees C. So why is it important that we're aware it's at 20 degrees C? Well, in the next tables underneath it, it tells you that copper has a positive temperature coefficient of 0.004 ohms per ohm per degree C. Now that's a factor that we apply to the resistance value of the cable from 20 degrees C. So we'd use that in cable sizing, but you can also use that after you have actually measured your conductors to find out what the resistance value might be at 70 degrees C. Okay, and you can utilize it for example, further investigation for air fault loop impedance values, where you have a circuit that possibly just fails your on-site guide rule of thumb values in Appendix B in the on-site guide, or in Appendix A in the guidance note 3. So copper has a positive temperature coefficient of 0.004 ohms per ohm per degree C. Okay. So in Appendix B in Guidance Note 3 or Appendix I in the on-site guide, you'll come across a table that looks similar to this, where we have our cross-sectional area of our conductors identified down column 1 for, in your tables it will say line conductor. And then in the second column, we will have either a dash or a different conductor size identified for your protective conductor in column 2. And then the third column there, you'll see there we've got the milliohm per meter value for the conductors. Okay, so either for one conductor or for two conductors. Okay, so looking a bit closer there, you'll see there we have a 1.5 millimeter squared conductor that has a 12.1 milliohm per meter value. Okay, a 1.5 millimeter squared conductor with a 1 millimeter squared conductor, as your, for example, an R1, R2 calculation, has a 30.2 milliohms per meter value. If you look at the first conductor there, the 1.5, 12.1, and you look at the 1 mil conductor at the top, all by itself, 18.1. If we were to add these two together, funnily enough, what would we get? 30.2 milliohms per meter. Yeah, so 12.1 plus 18.1 gives us 30.2, and it's that simple. Okay. So we'll try some basic cable calculations. So again, we're just going to be measuring a single cable. Okay, so it could be an R1 value, it could be an R2 value, just a single cable resistance. All right, it could be a main protective bonding conductor. That's one of the last ones we're going to do. So we have a 1.5 millimeter squared conductor. It is 15 meters in length, and we're looking to calculate its expected resistance at ambient temperature, either before or after we have measured the actual resistance. So a 1.5 millimeter squared conductor has a 12.1 milliohm per meter value. All right. So we take that information, we write that information down along with the length from the question, and we're looking to work out what its expected resistance is. And this is how we do it. We just take the milliohm per meter value and we multiply it by the length. Now, because we're using it in milliohms, I'm going to divide it by 1,000. Okay. If I wasn't using it in milliohms, I would need to, every time, take that 12.1 milliohms per meter and convert it back into ohms. So that would give us 0.0121 ohms per meter. Okay. that would give us 0.121 ohms per meter. All right, so that would be the value that I would utilise in the calculation if I didn't want to do the 1000 divided by 1000. But we're going to utilise the milliohm per meter value, just divide it by 1000. So we take 12.1 times 15, divide it by 1000, that gives us an expected resistance of 0.1815, okay? Now, what you need to understand with resistance, if you remember back to your first stage science, basic resistance calculation, series and parallel, you should be aware that if you increase the length of a conductor, its resistance is proportional to that increase. All right. So we have now here the same 1.5 millimeter squared conductor, but we've increased the length now to 30 meters. Okay. The last one was 15 meters. This one is now 30 meters. We have doubled the length. So back into the table, 1.5 millimeter squared conductor all by itself, 12.1 milliohms per meter is the value that we're going to now put into our list, but we're increasing that length from 15 meters to 30 meters. So again, write the calculation out, plug the numbers in, and we then have this resistance value of 0.363 as our expected value. If you look at it at 15 meters, you'll see that this value here is approximately half of what this value is. Why? Because we have doubled the length here to obtain this value. So that value there is double. Yeah, the 0.363 is double the 0.1815. Okay. Obviously, one of the things you need to remember is when you measure these, your meter for a low resistance ohmmeter will be giving you your values to 2 decimal places. Okay, so you might get 0.36, 0.37, or 0.18, 0.18, 0.19. Okay, depending on contact resistance and things like that as you're measuring your conductors. You need to take that into account as well. Okay. So now we have a 1 millimeter squared conductor. It's 20 meters in length. We're going to calculate its expected resistance at ambient temperature again. So we're back into the table. We have a 1 millimeter squared conductor. Its milliohm per meter value is 18.1 milliohms per meter. Okay. So we take that number, write it into our list, identify obviously our length, and we're then going to plug this into our calculation. So 18.1 times 20 divided by 1000. That gives us our expected resistance of 0.362 ohms. All right. Again, folks, basic first stage science information. As we increase the cross-sectional area of a conductor, its resistance is indirectly proportional. So it's not directly proportional, it's indirectly proportional. So here you'll see we have increased the cross-sectional area of the conductor from the last question from a 1 millimeter squared conductor to a 4 millimeter squared conductor. Okay, the length is still the same length. So we go back into our table and we're looking at the 4 millimeter squared conductor. You'll see there that's 4.61. Okay, now it's not quite a quarter of the value of the first cable. That's because the value of the cable, the resistances that we're dealing with, are that small that there are some slight discrepancies in this table because generally we're going to 2 decimal places. Okay, so in your table this one will say 18.10 milliohms per meter. All right, so there's just a slight discrepancy between them, but not a massive variation. So 4.61 and 20 meters. Take that information, plug it into our calculation. So 4.61 times 20 divided by 1000 gives us 0.0922. Okay, and if we take these two values here, you'll see there that the 4 millimeter squared conductor is roughly a quarter of the 1 millimeter squared conductor's expected resistance. Why? Because we have increased the cross-sectional area by a factor of 4, therefore we decrease the resistance by a factor of 4. Yeah. So, and again, the discrepancy is just because of how the values are obtained in the book. Okay. So we then have a 10 millimeter squared main protective bonding conductor, 27 meters in length. We're looking to calculate its expected resistance at ambient temperature, 20 degrees C. Okay. Into our table, we have our 10 millimeter squared conductor. Its milliohm per meter value is 1.83 milliohms per meter. Take that information and plug it into the calculation. So 1.83 times 27 divided by 1000 gives us our expected resistance of 0.049, 0.05 of an ohm. Okay. Generally, for main protective bonding conductors, we try to keep main protective bonding conductors down to what we consider to be in industry a negligible impedance. All right. Negligible impedance is 0.05 ohms or less. All right. When you measure that 27 meter long cable, you're expecting roughly 0.05 ohms if you have zeroed your leads, but you also then need to take in, due to contact resistance, another negligible impedance. Okay, so if that was a 27 meter length 10 mil conductor, then rather than 0.05 ohms as your expected max, you're then going to expect a max of 0.1 of an ohm. All right, that's taking into account contact resistance. All right. Hopefully that helps you with basic single cable resistance calcs. I'll do another one of these for R1, R2 values, and I'll do one for the ring continuity test as well. Okay, so onwards and upwards, folks.